Hello! In this video, we will cover derivatives and integrals of vector functions. Okay, let's start with derivatives. The derivative of a vector function is defined in the same way as the derivative of a scalar function. Okay, meaning if we have the derivative of a vector function, r prime of t, and using our alternate Leibniz format, dr dt, would equal the limit as h goes to 0 of r of t plus h minus r of t all over h. Okay, so that's the same definition if you go all the way back to Calc 1 that we use for defining the derivative of scalar functions, right? Instead of having an r with a vector function, we have f, and f and f and f. And so you go through and do the exact same thing that you would with a scalar function. All right, so what are the consequences of that? Well, so there's two consequences in terms of figuring out, what does that actually mean? What are the ramifications? So the first we're going to look at is the geometric consequence. So this will tell us, what is a vector function geometrically? What is the derivative of a vector function geometrically? So let's draw ourselves a picture. Make it nice and big. And let's say we have a vector function. This is r of t. Okay, so what would this produce on our vector function? What would this produce geometrically on our picture if we go through and calculate it? Okay, so first, let's go through and find the derivative at a specific point. So we're looking to find r prime at t naught. So we're going to need to have a specific value. So let's pick a spot and we'll say this is t naught. Okay. Then if you go through and plug t naught into this, all right, what do we, into the components, into the pieces here, what do you end up getting? So first, one of the pieces we're going to have is we're going to have r of t naught. So what is r of t naught? So r of t naught, so as we discussed in the last section, if you graph a vector function, it consists of all the terminal points from the vectors. However, if you go ahead and plug in a specific value, you will end up getting the vector that corresponds to that t naught value. So what we're going to end up with is r of t naught is going to be this vector here. Okay, so we've got r of t naught on our picture, and you could label that. That's r of t naught. Okay, and then let's go through and put r of t naught plus h on our picture. And in order to try and give ourselves some space, let's use a very large h. We'll say this point here corresponds to t naught plus h. So h would be the difference between these two values, in terms of the input value. Okay, so here's t naught. This would be the point t naught plus h. let's put that so if you go ahead and plug that in as a vector, all right, so r of t naught plus h would be that vector. So this would be r of t naught plus h. Okay, and then what does this ask you to go through and do with those? It asks you to subtract them. So all right, so we've got that on there, we've got that on there, and now we want to go through and figure out what's r of t naught plus h minus r of t naught. Okay, so if you take two vector functions, if you take two vectors and subtract them, what ends up happening? You end up getting the vector that points between the end of their terminal points. All right, so it's going to be between their terminal points, and it points in the direction of the positive one. All right, points in the direction of the positive one. So we get this. Now, actually, let's use a different color. So you get that vector there. Okay, and so that's that piece. And then the last piece is you divide by h. Okay, so we're going to ignore that just for the moment, right? So h is some quantity. You could say it's 2 or 5. And in terms of what it ends up doing is it's going to change the length of this vector. So it might make it a little bit shorter, or depending upon the scale, it might make it a little bit longer if h were less than 1. But in terms of the direction of h is not going to change direction. It's just going to change length. And so we're just going to ignore that factor for the moment, just for simplicity's sake. Now, it will come up in just a minute, but in terms of this initial vector, we're going to ignore it. Okay, so that's our those are our pieces: r of t plus h, r of t, and then the difference between them, calculated specifically for t naught, and you get this picture. All right, so now how do we go through and factor in the fact that we also want to take the limit as h goes to 0? Well, what we can do is we can go through and pick smaller h values. So let's say we picked h to be half the size, so half. So half, if it's half, it's going to be halfway between these two, right? So we could go through and say this point here. Oh, actually, let's go back to black. So this point here would correspond to t naught plus 1/2 h. Okay, and if you go through and plug that into your vector function, you're going to end up with this vector here. Okay, and then if you subtract those two, if we subtract those two, we're going to end up getting this vector. However, now I am going to take into account the fact that we took h and we made it half the size. If you put 1/2 in the denominator here, 1/2, then if you then go and simplify, take that 1/2 and you flip and multiply, you'll end up multiplying the vector by 2. So we've essentially shrunk the vector by 1/2, but we're going to multiply it by 2 when we adjust for the denominator. And so you're going to get a vector that's about the same length, but goes through those 2 points. So your resulting vector is going to look like this. Okay, so by plugging in shrinking h and making it half the size, then we'll end up, cutting the length along the curve by 1/2. But then when we plug 1/2 into the denominator, you'll end up multiplying by 2, offsetting that. And so you'll end up with a vector that's about the same length. It's just going to go through these 2 points instead. All right, and so the first vector, this corresponds to our initial h. We've made h half the size, and we get this vector instead. What if we go through and make h even smaller? Let's go through and plug in t naught plus 1/4 h. Okay, then we'll end up with this vector when we plug t naught plus 1/4 h into this piece. Right, so r of t naught plus 1/4 h is going to produce this vector. And then again, when we go through and take this piece, which is r of t naught plus 1/4 h, and subtract r of t naught, that's going to be subtracting these 2 vectors. Okay, and so we're going to get the vector that points between the 2 of them. And then the fact that we've taken a quarter h, if we put a quarter h in the denominator, when you flip a multiply, it's going to end up multiplying the vector by 4. And so that's going to prevent the vector from getting any shorter. It's going to be the same length as these first two. It's just going to go through these 2 points instead of those 2 points or those 2 points. Okay, and so we can go ahead and represent that in our picture. So we'll end up with this vector. Okay, and so if you look at what's happening here, so we started off with this vector, then went to this vector, then this vector. All right, you can, if you think about it in terms of calculus, right? So we cut through the curve, right? So this is a scalar line, right? So we cut through the curve in 2 spots, and then as we, we cut through a large part of the curve. Then we cut through less of the curve for these 2 points here. And so as we're moving along h, we're cutting through less and less of the curve. And so as h gets smaller and we get closer to t naught, you can see here for this last one, if you look really closely, we're only cutting through the curve for this short little piece. And so if we took an even smaller, like 1/8, we would cut through even less of it. And so eventually, as h goes to 0, you're not going to cut through the curve at all. You're not going to hit the curve twice at all. You're only going to hit the curve once. And as we recall from calculus, if you only hit the curve once, that's our definition for a tangent line. Okay. However, in this case, these are not lines, these are vectors. And so what you're going to end up with is you're going to end up with the tangent vector. And so let's go ahead and put that last here on here. So it looks like the tangent vector here is maybe going to be right about like that, something like that. And so you can see we're approaching, as h goes to 0, we approach the vector that is tangent to the curve. Let's just write that down. As h goes to 0, result is the tangent vector. Okay, and so that's the geometric consequence of going through and just using our regular definition from Calc 1 for defining, vector derivative of a vector function, is that it produces a tangent vector. So that's great, right? Because if you think about our result from Calc 1, it produces the slope of the tangent line. Vectors act kind of like slopes, and so we end up with the tangent vector is kind of like finding the slope of a vector function. Okay. So next, the second consequence is in terms of actually going through and calculating it, right? Algebraic, we could go through and look at the algebraic result. So if we've got r of t and it equals f of t, comma g of t, comma h of t, then if we say r prime of t equals the limit, and I'm going to change from h, because we have an h over here, I'm going to change, as h goes to 0, I'm going to change it into change in t. So this is an alternate format that you sometimes see for going through and calculating derivatives. Instead of using h, they'll use change in t. Okay, so this is our definition. First for r of t, and then for the derivative, just copied from the previous page. So we're saying that we're going to use the Calc 1 definition for the derivative of a vector function, and here's our Calc 1 definition. Okay, so what are the consequences of that? What happens when we go through and actually try and calculate this? That's the point of this algebraic part, is what happens when we try and calculate this. Okay, well, so what you can do is you can take the vector function here, you can take the input and you can plug it into the vector function, and well, you'll see what happens. All right, so what happens if we do that? All right, so if we take t plus change in t and we plug it in for t, we'll end up with f of t plus change in t, g of t plus change in t, and h of t plus change in t. Okay, and if we go through and r of t, let's just substitute that the vector for that. So this is the vector, so just substitute that in. We get f of t, g of t, h of t. Okay, and then let's actually use the line tool here. Hard to draw a straight line that long using the writing tablet. And then we have change in t in the denominator. And next, if you have the difference between two vectors, what do? To subtract two vectors, you subtract component-wise. So we'll end up with the limit as change in t goes to 0. This is f of t plus change in t minus f of t, comma g of t plus change in t minus g of t, and h of t plus change in t minus h of t. Okay, and then we'll have change in t in the denominator. And then, so the change in t here in the denominator, that's just a scalar quantity. Yes, it's a scalar quantity that's going to 0, but it's just a scalar. And as we discussed earlier with our definition for vectors, if you have a scalar, now it's divided by a vector, but you can change division into multiplication by just multiplying by the reciprocal. We could go through and actually take that scalar and multiply it into our vector. And the way that you multiply vectors and scalars is you take the scalar and multiply it by each of the components. So let's do that next. And okay, again, we're going to multiply by the reciprocal here. So if you multiply by the reciprocal of change in t times each of the components, this is what you get. And then finally, as we defined in the last section, the way that we take the limit of a vector function is by taking the limit of each of the components. So the limit effectively distributes, and so we end up with the limit as change in t goes to 0 of f of t plus change in t minus f of t over change in t, limit as change in t goes to 0, g of t plus change in t minus g of t over change in t, and the limit as change in t goes to 0 of h of t plus change in t minus h of t all over change in t. And so what happened? We ended up with our Calc 1 style derivative definition for each of the components. And so if we take the limit as change in t goes to 0 of this quantity, well, that's f prime of t. And the limit of this is g prime of t. And this guy is h prime of t. And so the consequence of using our Calc 1 definition for going through and calculating the derivative of a vector function is that the derivative of a vector function is just the derivative of the components. How spectacular is that? How nice is that? Okay, so let's go through and do a couple examples related to this so that we can just practice and make sure that we recognize that result. All right, so let's say we're given that r of t equals 1/3 t cubed, natural log t and sine t. And there's two instructions here. A, find r prime of t, and B, find r prime of 1. Okay, so let's first, step one, we need to go through and find r prime of t. And what was our previous result? Our previous result just said if we wanted to go through and find r prime of t, just take the derivative of each of the components. It's that simple. Okay, so the derivative of 1/3 t cubed, we bring the 3 out front, subtract 1 from the exponent, and you end up with t squared. The derivative of natural log t, 1 over t. The derivative of sine t, I don't know why I drew that comma so high. The derivative of sine t is cosine t. Okay, and so there's our derivative of our vector function. Again, to take the derivative of the vector function, just take the derivative of the components. It's that simple. Okay, and then to go through and find r prime of 1, what would that be? Just plug in 1 for the t values, right? So we're going to get 1 squared, 1 over 1, cosine of 1. And so 1 squared is 1, 1 over 1 is 1, and cosine of 1 is, yeah, well, it's whatever it is. Cosine of 1 is, plug that into a calculator, and you can figure that guy out. All right, so that's the first example. We can go through and just, very simple to find the derivative vector function. Just take the derivative of the components, and if you need to find the derivative vector function at a point, at a t value, just plug that t value in. Okay, let's do another example. So this example is a common example that you encounter in these derivative of vector functions chapters. Maybe example is not the right. It's an application. Okay, so let's say r of t is t plus 1 comma t squared, and you're asked to go through and find the equation of a tangent line. Right, to r of t at t equals 1. So this is a common example that you encounter when you first learn about derivatives in Calc 1 as well. So there's a lot of similarities like that between the two courses. So Calc 3 is like an echo of Calc 1 in that way. And so when you're in Calc 1 and you need to find the equation of the tangent line, you use the derivative to find the slope, right? And then you combine the slope with a point, right, using point slope form. So we want to have the exact same approach here, right? So first we need to go through and find the point. So they gave us a t value, but they didn't give us the point. So we don't know where, we don't know what point on the curve corresponds to t equals 1. To figure that out, you can actually just take t equals 1 and just plug it in, and it will end up producing the vector. And again, so the way the graphs with vector functions work is that the graph of a vector function is just all the termination points. So if we plug in t equals 1, we're going to produce a vector whose termination point is going to be the point that lies on our tangent line. So if we just take 1 and plug it in, you get 1 plus 1, 1 squared, and so we get 2 comma 1, right? And so that's going to be the point that's on our line. Okay, and then in Calc 1 we found the slope to go with our point. In this class we're going to find the tangent vector. Okay, the tangent vector x, kind of like a slope does, right? So to go through and find the tangent vector for our tangent line, we need to go through and first find r prime of t, right? Because this produces a formula for tangent vectors. All right, this produces the tangent vector for any t value. And to do that, we just calculate the derivative, and derivatives are component-wise. So we take the derivative of t plus 1, that's going to be 1, and the derivative of t squared is going to be 2t. And then once we have our function essentially here for going through and finding the derivative anywhere, we want the derivative that corresponds to t equals 1. So this is going to produce the tangent vector at t equals 1. Okay, and so the tangent vector is going to be act like our slope. So we're going to get 1 comma 2 for that. and then you can put those two together, right? So now we've got point, we've got tangent vector, and then the line equation, you just combine the two, right? We want to combine the slope, the point with our direction vector. And so we're going to get x equals 2 plus 1 times t, and y equals 1 plus 2 times t, right? So I put the point here and the tangent vector as a direction vector for the line here. Okay, now you can tie all of this stuff together by drawing a picture. I actually think this is a good practice to do when you're first learning about tangent vectors. Okay, so let's see if we can tie all this together by drawing a picture and putting all of this stuff onto our picture. So that would be like a second part to this if we had this is part A. So part B, draw a picture. Okay, so to go through and draw a picture, first we need to graph the vector function. So in the last section, we went over how to do that. So if we have x, you set x equal to the x component, and you set y equal to the y component. Okay, and then you want to go through and eliminate the parameters. So to eliminate the parameter here, the easiest way to do it would be to solve for t in this first equation. So you get x minus 1 equals t, and then take that and plug it in. Okay, and then you're going to have y equals x minus 1 squared. Okay, and then once you've done that, you can then go through and graph that, right? So that's going to be the regular parabola that's shifted 1 to the right. So we'll have 1 right there, and then point here, and then we could draw our curve. Let's see if we could do it. Oh, that's the best we could do with the writing tablet, and then I missed by a little bit. That's okay. We'll just we'll expand it. There. Now it hits it. Okay. And so, right. So next, if we go through, and so t equals 1, that ended up producing 2 comma 1. If you take 2 comma 1 and actually put it onto your picture here, that's this vector here. So here's the vector 2 comma 1. So that point, this point here, is the point that corresponded to t equals 1, okay, on our picture. So don't get confused, right? This is x equals 1. This point here corresponds to t equals 1, right? They are not the same. I mean, in particular, you can see x is equal to t plus 1. Right, and so we can go through and next we can graph the direction vector. So at that t equals 1, so we went through and we found the tangent vectors. We said the tangent vector is 1 comma 2. So right, what would that look like? Let's use a different picture here, different color here. So 2 comma 1. Well, if this is 1 unit, right, then if we went 1 unit over from there, we went 1 unit over and then up 2, we would get something that looks about like that. Right? So that's about 1 over 2 up, 1 over 2 up. And so, we take, so this vector here ended up getting us to the point, and then this vector here ended up getting us the direction vector. And if you put all that together in your line equation, you end up with the line that goes through the point with direction vector given by the tangent vector. And so that's a classic application problem that you encounter in an introductory vector function section, is going through and finding the equation of a tangent line. And that's how you do it. So just one more time to recap, you find the point by plugging the t value into the vector function, and then you find the tangent vector by finding the derivative of the vector and then plugging the t value into the derivative. And then you take the point and the tangent vector and you put them together into the line equation. Point, direction vector. So the direction vector is the tangent vector. Okay. Next, we're going to look at something called the unit tangent. Oops, let's go back to black. So the unit tangent it's just a definition. It's a tangent vector of length 1. So one unit as in unit vector. Okay, and so the way that you find the tangent vector is you take the derivative of the vector function and you divide by its length. So it's essentially just a normalized tangent vector. And normalize is the name for going through and taking a vector and dividing by its length. So r prime by itself is the tangent vector, and if we then divide by its length, then we'll end up with a tangent vector that's also a unit vector, and that's called the unit tangent. Okay, so example, let's go through and find the unit tangent for the last problem we just did, right? So we have r of t equals t plus 1 comma t squared, and we want to find the unit tangent. Okay, so to do so, you need to calculate this thing on the right hand side here. We need to calculate this. All right, so to do that, you need to first have r prime of t, and so you get 1 comma 2t, and then you need to have the length of r prime of t, which is the square root of the component squared. And then the unit tangent is just divide those two, right? So we get 1, 2t over the square root of 1 plus 4t squared. This is just a scalar quantity in the denominator, and so you can divide it through by multiplying by the reciprocal, and so we end up with 1 over the square root of 1 plus 4t squared, comma 2t over the square root of 1 plus 4t squared. And there you go. That's your unit tangent. So this gives us the unit tangent for any point. Now, if we want it, or for any point, for any coordinate, right, that has t, any input t. So we can go through and plug in a t value to find a unit tangent. So we could plug in 1, just like we had in the previous problem. And if you plug in 1, what happens? You get 1 over the square root of 1 plus 4, so that's going to be 5. And then 2 times 1, that'll be 2 over 1 plus 5, so square root 5. And so we end up with t of 1 produces the vector 1 over root 5, 2 over root 5. And so the question is that a tangent vector? Is that tangent? Well, what did we get when we did this problem? We got 1 comma 2. So anything that's in the ratio of 1 comma 2 is going to be parallel, so it's going to be the same direction. So this has the same direction as the tangent vector. However, what is true about it? Well, if you check, it has the same direction as the regular tangent vector, but guess what? It is length 1. Okay, so we ended up with a tangent vector that is length 1. Okay, and so that is the unit tangent. Okay, next, we're going to look at antiderivatives. Slash the indefinite integral. So these two things are two sides of the same coin, right? They're the same idea. And so what we can infer from this, if the derivative is calculated component-wise, right, then the antiderivative, which is the opposite of the derivative, is also going to be calculated component-wise. Okay, so just writing that down. So we can go through and verify this to ourselves by just using the definition of antiderivative or an indefinite integral from Calc 1, but applying it to a vector function, right? So what does it mean to be an antiderivative of a function? It means that if you took the derivative of that function, of the new function, then you'd get the original, right? So if I say, what is the antiderivative of little f, then capital F is the antiderivative if the derivative of capital F equals little f. Okay, so let's just write that out, except with our vector function. If capital R of t prime equals little r of t, then capital R of t is the antiderivative. That's what I just said, just written out, and I used R instead of F. Right? We use F for scalar functions. Right. So if you wanted to translate this into the equivalent for scalar functions, we would say if capital F prime equals lowercase f, then capital F is the antiderivative of lowercase f. And that's our definition for an antiderivative. It's the thing that you would differentiate to get the original function. Okay. And so let's go through, and we can use this definition just to verify it to ourselves, right? So we'll verify this to ourselves. So if we go through and say, let capital R of t equal capital F of t, capital G, there should be no line here. It's not a vector. It's a component of a vector. And capital H and lowercase r of t equal lowercase f, lowercase g, and lowercase h. Right, given these two, we can go through and first we can find our capital R prime, right? So we can find this, right? Then capital R prime of t would equal capital F prime of t, capital G prime of t, capital H prime of t, right? That's what we just learned just a few minutes ago, is that the derivative of a vector function is the derivative of the components. All right, so given these two things, we can infer this. And then if we know that R prime equals F equals lowercase r, since R prime of t equals lowercase r of t, right? So what does that tell us? Since this equals this, it tells us that so equality for vectors means that the components are equal. So since this equals this, since capital R prime equals lowercase r, that tells us that capital F prime equals lowercase f, and capital G prime equals lowercase g, and capital H prime equals lowercase h. So we have F prime of t equals lowercase f, G prime of t equals lowercase g, and H prime of t equals lowercase h of t, right? That's by vector equality. If two vectors are equal, then their components have to be equal, okay? And then if capital F prime equals lowercase f, and capital G prime equals lowercase g, and capital H prime equals lowercase h, then what does that tell you? It tells you that capital F is the antiderivative of lowercase f, capital G is the antiderivative of lowercase g, and capital H is the antiderivative of lowercase h. All right, so capital F, oops, no vector again. Capital F is antiderivative, we'll just leave that, lowercase f. Oops. I'm trying to squeeze this in here. Capital G is antiderivative of lowercase g, and capital H is antiderivative of lowercase h. And that completes the explanation. That completes the proof. That's what we said. The antiderivative of a vector function is the antiderivative of the components, well, not the integral components, Sorry. Oh, shoot, that actually was right. It's the indefinite integral of the components. Oops, that was correct. Of the components. That's the word that was missing, of components. Okay, and so this goes through and proves this result, that if you're going to go through and if the derivative of a vector function is the derivative of the components, then the antiderivative of the vector function is the antiderivative of the components. It just kind of fits together and makes sense. And this is just kind of the explanation that shows that is true. It's not just sensible, but it's correct. Okay. So, just to use our indefinite integral form, which is the way that we represent antiderivatives, in the indefinite integral form, what we would say is that given r of t equals f of t, g of t, h of t, the integral, the indefinite integral of r of t dt, right, is going to be the integral of the components. Whoops, give myself a little more space there. It's going to be the integral of the components. So that's what that previous page was saying, if you're having trouble following that. Is that the antiderivative of the components of a vector function, antiderivative of the vector function is the antiderivative of the components. And that's what this says. The indefinite integral is the same thing as the antiderivative. So the indefinite integral of the components, the indefinite integral of a vector function is the indefinite integral of the components. Okay, that's a mouthful. All right, let's just see an example. Hopefully that will clarify things. All right, so if we've got the integral of sine ti plus t squared j plus 1 over tk dt. All right, so you're asked to go through and find the antiderivative or indefinite integral of a vector function. And you just tack on a dt here, right? That's the left-hand side. What you do is you just apply the integral to each of the components. All right, so the way you're going to do that, you get the integral of sine t dt times I plus the integral of t squared dt j plus the integral of 1 over t dt k. And right, so the antiderivative of sine t is negative cosine t I. The antiderivative of t squared is t to the third over 3 j. And the antiderivative of 1 over t is natural log t. Okay. All right, so that shows how simple it is to go through and find an antiderivative. Is if you're asked to find the antiderivative of a vector function, you just find the antiderivative of the components. Okay. So I did one more example here just to show you a harder one. It may be a while since some of you have calculated an integral, a more difficult integral. So I've mixed in some u substitutions and integration by parts. Just for practice. All right, so if you're asked to go through and find the antiderivative or indefinite integral of a vector function, then you just find the indefinite integral of the components. Oops. Don't forget that dt. All right. Now, so the easiest way to do this would just be to do it off to the side and then come back and just pop it in here. So, yeah, let's just do it on the next page and then we'll just transcribe it back to this page. All right. right, so what do we have? We have the integral of t 1 plus t squared to the third dt. Okay, so this is a classic u substitution, right? U is going to be the function that's inside here, and then du will be our derivative. So anytime you're looking to integrate a function, and it doesn't fulfill one of the classic function formulas, then you'll be looking to manipulate it to make it look like one of those formulas. And what do I mean by the classic function formulas? I mean, like if you had, t to the n, right? So if we have t to the n dt, we know that's going to be t to the n plus 1 over n plus 1, right? And we'll throw a plus c on there. So if it doesn't look like this, then you've got to manipulate it to make it look like this. And if you look at this one, it does not look like this. So we need to do some manipulation. And if you have to do that manipulation, one of the tools is a u substitution. And anytime you do a u substitution, you're looking for something that if you differentiated it would be in the problem. Okay. And so in this case, the fact that the derivative of this is right here is a key sign that this is going to be your u. Okay, so that's one of the little rules of thumb that can help you in identifying the u in a u substitution problem. Okay, but yeah, so we want to just do u equals 1 plus t squared. Then du is going to be 2t dt. And then at this point, we need to go through and translate this original integral over into an integral in terms of u. And there's a couple ways you can do this. The way that I do it is I build up this so that it has all of this stuff in it, right? So right now it already has the u in it, but it doesn't have the du. It doesn't have a 2t dt. It has a t, but it doesn't have a 2t dt. So to get the 2, I'll go through and multiply it by 2 and offset it by multiplying by half. It might help maybe to use a different color for that. So just to kind of keep track that we have added that. Okay, so that's the way that I do it. If you want to solve for dt and then substitute, you can do it that way too. I don't like that method as much, but yeah, do whatever works for you. Okay, and then so here we're going to get, so we're going to translate everything. So this is going to be u, so we're going to get u to the third, and then the 2t dt, that's our du. So we can just substitute. And now take a look up. Now it does fulfill one of the classic formulas. And so we can go through and do u to the fourth over 4 plus c. Okay, and we'll end up with u to the fourth over 8 plus c. And then you can substitute your u back in, and you'll get 1 plus t squared to the fourth over 8 plus c. Okay, and so that's going to be our antiderivative, or our indefinite integral for that function. Okay. Next, let's go through and do the antiderivative for sine t dt. And yeah, we'll just do it on the same page here. Or sorry, sine t cosine t dt. And so here, this again is not one of the classic formulas, right? So we need to manipulate this. And the manipulation you can do is, as we just discussed, if you see a function and its derivative, then you can try to do a u substitution. So cosine is the derivative of sine. So you could do u equals sine t, then du equals cosine t dt. And then we can just take all that stuff and pop it in. And so we get u du. And this is one of the classic formulas. And so we'll get u squared over 2 plus c. And so we get sine squared t over 2 plus c. Okay. All right. And then the last example we have, what was it? T sine t. dt. And so this this, we don't have a function and its derivative. So this is not one of our classic integral formulas, and we don't have a function and its derivative. And so the next thing that you look for in terms of your integration techniques is, do we have a product, right? If you have a product, then you can use integration by parts. And we do have a product, t times sine t. And so we could try to do integration by parts. And so integration by parts, set u equal to t, dv equal to sine t dt, then du equals 1. Well, 1, it's going to equal dt, 1 dt. And v equals negative cosine t. And then from there, you just use the integration by parts formula, which is that this equals u times v. So we're going to get negative t cosine t minus the integral of v du. So that's negative cosine t dt. And so we get negative t cosine t plus the integral of cosine t dt, which is going to be plus sine t. And then you can throw a plus c on there. Okay, and so we've got our 3 results, and now it's just a matter of popping them in onto the previous page. So 1 plus t squared to the 4th over 8. So we're going to have 1 plus t squared to the 4th over 8. Okay, so that's going to be our first result. I'm going to leave off the c's because I'm going to show you at the end what you can do with those. And then sine squared over 2. And then negative t cos t plus sine. And then what you can do is you can add a vector c, okay, a vector c. So this is just a vector that's filled with constant components. And so this is still going to be the antiderivative for this, because if you differentiate this whole thing, the derivative of this is going to give these components, and then the derivative of our constant vector is going to be 0. Okay, and so that's one way that you can handle the plus c, is by adding it off to the side like that. Okay. Next, we have definite integrals. Okay, so the definite integral is defined, the definite integral of a vector function is defined the same way as the definite integral of a scalar function. In particular, what is that? So we don't use this one very often, just like we don't use the limit definition for a derivative, but the integral from a to b of r of t dt is equal to the limit as n goes to infinity of the summation I equals 1 to n of r of t sub I star change in t. Okay, so that's our classic definition. If you go back to the definite integral in Calc 1, that's how we defined it, except of course we'd have f of x dx, and f of x change in x. But other than that, it's exactly the same. We just have changed over from f to r and from x to t. Okay, so what are the consequences of this definition? Well, similar to what we did with derivatives, you can go through and by just manipulating this, you can figure out what the consequence would be in terms of calculating a definite integral of a vector function. Now, the write-up is kind of long, and so I'll go on to the next page and just skip ahead. You can see, I'll show you it. All right, so what we're going to do is we're going to start off and we'll say, given that r of t, it might even take 2 pages, given r of t equals f of t, comma, g of t, comma, h of t, then the integral from a to b of r of t dt is going to equal the limit as n goes to infinity of the summation. Let's try that again. The summation symbol is kind of hard to do. From I equals 1 to n of r of t sub I star, change in t. Okay. Well, so first thing that we can do, we can use our vector function definition here and to just take this and just pop it in. And so we can rewrite this. Actually, I'm going to move that up even higher. I'm going to try and squeeze this onto a single page. So we have limit and write small as n goes to infinity, summation I equals 1 to n. And this is going to become f of t sub I star, comma, g of t sub I star, comma, h of t sub I star, change in t. And now, since this change in t is a scalar quantity, you can multiply it, multiply your vector function by it by multiplying it by each of the components. So we'll get the limit as n goes to infinity, summation I equals 1 to n of f of t sub I star, change in t, comma, g of t sub I star, change in t, comma, h of t sub I star, change in t. Okay, and now the next part, right, is what we'd like to be able to do is take this summation and bring it inside here. However, it's not completely obvious that happens. You could go through and infer, all right, so the way that you add vector functions is you add component-wise. And so because of that fact, you could just take, the component-wise sum, you could just take a sum and bring it inside. But that's a little hard maybe to infer at this point. So to make that clear, what you can do is you can actually just write out the sum, and then that will become more obvious, right? And so that's what we're going to do next. That's why I need so much space here, is because I'm going to write out the sum here. So the way the sum works is you're going to go through, the way the sum works, you're going to start off with I equals 1, plug it in, then add I equals 2, plug it in, then add ... through I equals n, plug it in. And so we're going to end up with f of t sub 1 star, change in t, g of t sub 1 star, change in t, h of t sub 1 star, change in t, right, plus the next one, f of t sub 2 star, change in t, g of t sub 2 star, change in t, and h of t sub 2 star, change in t, plus, right, f of t sub n star, change in t, g of t sub n star, change in t, and then h of t sub n star, change in t. Okay, and now it's a little bit clearer, right, that if you wrote this out this way, if you're going to add all of these, you add component-wise with vectors. So we would add this to this to this, this to this to this, this to this to this. And so we would end up with limit as n goes to infinity, let's see, how did I do this? All right, so we're going to have this. So we're going to have f of t sub 1 star change in t plus f of t sub 2 star change in t plus dot 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 plus f of t sub n star change in t, comma, and then the next line we'd have g of t sub 1 star change in t plus g of t sub 2 star change in t plus dot 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 plus g of t sub n star change in t, comma, h of t sub 1 star change in t. It's a little tedious, but it just makes it very clear that the summation does end up distributing onto each of the components, right? And if now that we've done that, we can see, oh, well, what is this? If I take the, f of t sub 1 star plus f of t sub 2 star through f of t sub n star, well, that's the same thing as going through and using the summation notation, sum f of t sub I star change in t, where I equals 1 to n. And then this is the same thing as the, using the summation notation, I equals 1 to n of g of t sub I star change in t. And then this here is the same thing as the summation I equals 1 to n of h of t sub I star change in t. Okay, and then we're almost there, and it looks like maybe it's going to fit. So the last thing is, how do you take the limit of a vector function? You take the limit of the components. And so we're going to end up with the limit as n goes to infinity of the summation I equals 1 to n of f of t sub I star change in t, the limit as n goes to infinity, summation I equals 1 to n g of t sub I star change in t, the limit as n goes to infinity, summation I equals 1 to n h of t sub I star change in t. And then what happened? We ended up with our Calc 1 style definition for an integral on the first component and the second component and the third component. And so let's see, maybe I have a little more space right here. So this equals the integral from a to b of f of t dt, comma, the integral from a to b of g of t dt, comma, the integral from a to b of h of t dt, right, as a vector. And so, long story short, just like the derivative, just like the antiderivative indefinite integral, the definite integral of a vector function is also the definite integral of the components. It does kind of make sense that it would be consistent like that, right? Okay, let's do an example. All right, so let's say you're asked to go through and find the definite integral of this vector function. The way that you do that is you find the definite integral of the components. All right, so our antiderivative here is t squared over 2. Our antiderivative here is t to the 4th. Our antiderivative here, 2t. And we end up with 4 over 2 minus 0 over 2, so that's going to be 2. 16 minus 0, 4 minus 0. And that's how it works. And so we're able to go through and find the definite integral of a vector function by finding the definite integral of the components. Okay, so that's the topic. That's the video. Vector derivatives and integrals of vector functions. I hope you enjoyed it. Thank you for watching. See you next time.